Hi, I'm Deepak. Today I'll be presenting our paper towards memorization estimation, fast, formal, and free. In this paper, we try to understand memorization. We introduce cumulative sample loss and efficient proxy. It is simply the accumulated loss of each sample over the entire training process. We establish a theoretical framework that connects CSL to both learning time and memorization. We show that CSL is about 10,000 times faster than stability-based memorization, and we show practical applications such as identifying mislabeled examples and duplicate detection in which CSL achieves state-of-the-art performance. Let's think about the intuition and talk about CSL. This plot plots the loss trajectory of two samples over the course of training on the ImageNet dataset. The green one shows an easy example where the loss drops very quickly and stays low during the entire training process, whereas the hard example is learned much later during training, where the loss stays high and is learned much later during training. While the loss value fluctuates, the average loss plotted in green and yellow dashed lines clearly show that easy examples which are learned early have an average or cumulative loss which is much lower compared to a hard example. This forms the basis for our proxy. We formally define three terms: cumulative sample loss, sample learning condition, and learning time. Sample learning condition refers to the fact that the input gradient, or the gradient of the loss with respect to input, must fall below a certain threshold, the expected gradient with respect to input, which is nothing but the sample learning condition. Learning time is the earliest iterate at which the sample learning condition is met. Our theoretical results are based on the following assumptions. First, we assume the loss is either cross entropy or bounded. We assume Lipschitzness of the loss function, a bounded gradient variance, and an unbiased gradient estimator. We provide the following results. First, we show that the input gradient norm is bounded by the weight gradient norm. Secondly, we show that the input gradient must converge as SGD continues. Thirdly, we show that learning time bounds memorization. Next, cumulative sample loss bounds learning time, and finally, CSL bounds learning time. We validate our theory on CIFAR 100 and ImageNet datasets. If our theory was correct, we would see a linear relation on CIFAR 100 and ImageNet datasets. We clearly see that on both CIFAR 100 and ImageNet, we see a linear trend between memorization and learning time. So test our CSL and learning time bounds, and we clearly see another linear relation. We also test CSL and memorization bounds. Here we see a slight non-linearity towards the end. This is explained by a previous paper which talks about the fact that the loss bound is not uniform across the entire memorization range. Thus, accounting for that makes it more linear. Let's look at some quantitative results in terms of similarity with memorization. Here we take few other proxies for memorization, such as final epoch sample loss, curvature, loss sensitivity, forgetting frequency, and we compare it with our metric, and we show its similarity to stability-based memorization from Feldman and Zhang's pre-computed scores. And the table lists both cosine similarity and Pearson correlation, where we clearly see CSL achieves the highest correlation performance. Using CSL, we can apply a threshold and identify mislabeled examples in the dataset. And by introducing a label noise, we clearly see that CSL can identify mislabeled examples and achieve state-of-the-art performance on CIFAR 10 and CIFAR 100 datasets. Additionally, it can also identify duplicates in the dataset. In summary, we understand memorization in this paper, propose an efficient proxy, and show practical applications. Thank you.